Good afternoon, everybody. I think it's about time. Just wait until the half hour comes up before we begin. Okay, so my name is Neil Voce. I hope you can all hear me. Maggie, can you confirm that you can hear me from there? You can't hear me. Okay, that's problematic. And unmute.
I can hear you now.
Oh, you can hear me now. That's good news.
I don't know, Maggie. This is Robert. I can hear you.
Hi, Robert. Well, I'm sure if you can hear me, then everyone can probably hear me. Okay, so this afternoon we are going to discuss PAVA systems for airports. My name is Neil Voce. I'm in business development at Ambient System, and today's discussion about PAVA systems for airports contains some slightly more advanced concepts, which I don't think we're going to have the time to really go into the detailed working of all those things today. But what I want to do is just sort of give you a bit of an overview of some of the principles that are in play there, and then you know, if anyone wants you to go into that stuff in more detail another time, would be very happy to continue with that conversation somewhere else. So hopefully everybody can now see the presentation slides. And so PAVA systems for airports. Let's crack on. So we're going to discuss PAVA systems in transport applications, the requirements around those in airports, the point of using a PAVA. We're going to have a little look at system architecture for PAVA, and we are going to discuss a little bit about acoustics and that type of thing. So with no further ado, let's move on to the first proper slide. So here we sort of start to look at a kind of complicated diagram over on the right hand side there, showing how once you start to look at a bigger transport facility, you might have a whole selection of integrated services floating around the LAN. And that integrated approach is going to benefit, going to benefit everybody, the operators, in terms of them being able to communicate generally across a wider area, or perhaps in fact over a smaller area. And also it's going to mean that there's a good selection of simple information available to passengers and so on in the transport facility, whether it's whether it's an airport or a large station. But we're concentrating on the airport terminology for today. And going back to the sort of the basics of this is what is it that we're doing with a voice alarm? And it comes back to the idea that if you sort of use sounders, bells, signs, people don't tend to take as much notice of those as they do with a voice message. Obviously a bell or a sounder can only just make a tone. It doesn't tend to give any detailed instructions. And you know, in an airport or something, particularly in an airport, I mean, people are there, maybe they only go there once a year, maybe they only go there once every couple of years, so they're not necessarily that familiar with the building, don't really know where places are, where the nearest exit is, for example, is very much not obvious once you're in an airport and you've gone through security and this, that and the other. So you know, there's you do need to give people unambiguous instruction in order to avoid people doing the wrong thing or beginning to panic, which obviously, you know, we don't want to get to the stage where we've got panic breaking out in our airport terminal. So the PAVA system's main features, obviously we are designing this system to work in the emergency situation. So the performance of that system and the equipment that we use in the European area will have been standardized under the EN54 banner. So we have all our equipment, whether it's power supplies, electronics or loudspeakers, will be proven to meet certain criteria under EN54 parts 4, 16, 24. Part of the performance of that system is also going to be meant to be guaranteed, so you're meant to be able to intelligible messages and so on. And the systems are going to be essentially self-monitored, so that if there are any issues with the system, those will be picked up internally and reported back to the user or maintenance services. And so now we've got ourselves a reliable public address system capable of transmitting emergency messages. And one of the things that we're going to discuss in this sort of conversation is how we maybe expand that out a little bit, and we use the PA system in conjunction with other things. And potentially in an airport, we might want some bi-directional communication instead of just unidirectional communication. So we've got our PAVA system, and what we're trying to do with that, so the messages we're trying to deliver is, first of all, we're increasing our traveller safety, high levels of reliability. We want to then give flight and general information. So we want to be able to manage the travellers and where they're going, so that we're giving them timely information to move to the area of the airport that, you know, is the next phase of their journey. We need to be able to integrate this PAVA system with a variety of other systems, fire alarm, obviously, flight information for messages about where aeroplanes are leaving from, and also PSIM, physical security management, and so on. And it's quite important with airport systems that these systems are scalable, because you can have multiple terminals, you can have outbuildings, and all of these may need to be brought under the general banner of the system. So, you know, there's a variety of different products that might be needed in different areas that might need to be covered in an airport. And so as we build the system up, as we said, we've got these EN54 part, broadcast of traffic from flight information. But then on the right hand side, as we put in these boxes here, we've got to give gate staff the ability to summon people to the gate. And we're going to look at the possibility of doing that with SIP paging stations here. And also throughout the airport, we may have some help points that enable travellers to request some assistance. So our system architecture begins to look a little bit like this, and the choice of equipment that we're putting in. So here we've got a relatively standard sort of pier type arrangement of an airport. I think on the right hand side here in the green, we're meant to be having our check-in areas, and then we're meant to go through security into the yellow and blue. I don't know if we're meant to be maybe having a cafe in the brown area, and then moving into the purple area where someone's parked our aeroplanes ready for us to go off on our holidays. And what we're seeing in that is we've got our security desks on the right hand side in the green area. So they've got relative fireman's microphones suitable for fire staff to make an evacuation from the whole airport. And then after that, we've mainly, our microphones at this point, we've decided to change those into SIP paging stations. So the SIP paging stations are going to give us a variety of more methods of communicating with different people. And also one of the reasons for going over to the SIP side of things is that then all that cabling can all be standard LAN technology. You haven't got to actually put in dedicated cabling for microphone points and so on. The choice of speakers here, you will see we've got some line array loudspeakers in the areas with a longer sort of reverb reverb time. We've got some pendant speakers in the lower ceiling areas, and also some ceiling speakers. And we've got these the little help points which you can see floating around here for people to be able to use. So this is the type of equipment that we are thinking in terms of the field devices, being intercoms, loudspeakers, ordinary microphones, and different loudspeakers to suit the actual areas. And then when you start to look at the broader scope of the airport as a whole, what we can see is that we may have, again, working kind of anti-clockwise around this, a main terminal building. So the main terminal building might have a full custom-built PAVA rack suitable for high power and many zones, having the fireman's mic and paging mics. The departure terminal is effectively very similar to the main terminal. So again, you've got probably a custom-built PAVA rack there. And then on the left-hand side, the piers, what we've used here, what we've suggested here is that these might be the sort of compact off-the-shelf type devices like the Ambient System MIDI-VES. So, that's 8 zones, 1500 watts, but it's available as a single unit. And then the whole thing, all these racks are all going to be fibered together. And then from the primary control and secondary control positions, we're obviously going to be able to reach down into all of those areas to make paging announcements or to oversee an evacuation. So the evacuation would be potentially manually run from the primary control center rather than being just an automated message. And in the event that there's some problem has befallen the control tower, we've got a secondary backup position as well. So again, this is pretty standard stuff with a larger airport to have a primary and secondary place to run the systems from. What we've talked about here is segmentation. So the point of this is that each of the segments of the airport should be able to function as a standalone system. In this case, that would mean that there would be a fire detection interface or interface to fire detection at each location, but that would be able to be overridden by the system function as a whole. But the fire detection would be there in the event that the segment became isolated. That segment would still be able to receive an evacuation contact and encourage people to leave the area. And what we're sort of saying here is, you'll notice the little red cross on the right hand side there is, we're saying that we don't necessarily believe that these islands, these segments, should necessarily be able to page from one to another. So from your operational command center, control tower, administration building, obviously you can reach each area, but in each segment you might choose not to allow them to communicate directly from one to another. And there are a couple of good reasons for doing this. The primary reason for preventing segments from being linked together is actually just, it's simpler to manage and maintain each segment individually if they don't interact. For example, if you have a fault indication on your system and they are only linked together by VLAN, then if you should happen to have a fault on segment A, you won't receive a fault light or indicator on segment B. So this makes fault diagnostics easier. It makes general maintenance easier. It makes it easier, for example, to do an upgrade on one segment by turning that system off overnight without necessarily affecting either of the other segments. And also, just in terms of land traffic, if you have a large airport and you have the whole thing connected together as one big system, and all the devices in the airport are constantly talking to each other to say, hi, I'm okay, are you okay? And all that requirement for fault reporting, plus a larger number of actual announcements and so on, you can just get to the stage where the system is quite congested. So it makes a lot of sense to segment these things down, and would be highly recommended. So just summarize that: increase cost efficiency by using smaller scale products, so using the MIDI-VES in the outlying areas. Reduce costs of installation by effectively having more local IP based nodes. Increase reliability, reduce downtime, reduces likelihood of false alarm spreading, and you can make responsibility in each segment to potentially even to different companies. If you had a very large airport where there could be different companies providing the maintenance in different segments. So that's a little bit on the sort of PAVA side of it. Then let's have a little think about the emergency intercom side. So we're providing these intercom units. We suggested, for example, seeing the ICDG1 a desk, a gate, and so by putting that at the gate, you can use the ICDG1. It has the ability to fire out a variety of pre-recorded messages to its zone. You can pre-code routing in it, so you can confirm if you just press a single button where that's going to route to. So it's very much the same as using a microphone, but does give you the advantage that in between times you can also use it as a telephone to communicate with other areas. So it's less clutter on these desks, because the desks aren't necessarily all that big, particularly in older airports where the facilities are a bit more crowded. And then on the left-hand side there, the ISO emergency 01. We can provide these type of typical passenger help point emergency points, maybe looking like that, but also available in a more distinctive help point type labeling. And so once we've provided these, we've decided to use these SIP devices in our network. What we're then going to do is we're going to connect them through our ISE comm server. That's effectively like a little telephone exchange with an interface to our voice alarm system. So it does all the things you would then normally expect it to do, monitoring the status of the intercoms to make sure everything's working. You can make schedules for the announcements, and you can record all the announcements that are made, and you can get a log of what announcements were made when to where. So it's giving you a nice little bit of data there for you to collect. So in this case, there's this system now focused on the gate idea. So we've got the ICDG1 connected over the LAN through the server into the MIDI-VES, and then going out to the loudspeakers at the gate. So kind of pretty much what we've just explained. And the ICDG1 has given the user something nice and simple to use, which we can pre-program with options on which zones are to be called, options on pre-recorded messages to use. We can also use call stacking. So call stacking can be quite important. So your person at the gate goes to make an announcement, and halfway through some other announcement is made somewhere else. So we can actually buffer up an announcement for wait for the zone to be available, and then the announcement is created. So the announcement is effectively held back until the zone is clear and ready to announce it. So that's actually quite an important feature in these type of systems where you potentially have many sources. I mean, it's not uncommon to have 50, 60 sources of audio in a large airport. So having a method of making sure you don't lose your announcements is quite important. So the general solution diagram, looking complicated, I know, but let's just take a moment and digest what we have in front of us. PAVA system, basically on the bottom at the right. So that's the overall PAVA system in our main terminal building. We've then got our mini-VES or MIDI-VES type systems maybe out at the gates there. and both of those are directly connected to the fire alarm system so that they can work standalone in segments. On the left at the bottom, we're showing that we've got data incoming from passenger information systems or flight information systems and PSIM, physical security integrated management. So we're potentially enabling a security desk to also work with our system. So at that PSIM terminal, the security office might have CCTV and so on, and access control. And then we're going to enable them to also come through our system to make security announcements into limited areas. I mean, these could be back of house areas, they could be perimeter fences, you know, lots of options there. And then looking at the top half of our diagram here, we've got the whole, you know, another whole gamut of options for inputs. So private mobile radios or walkie-talkies, mobile devices such as iPads and Androids coming through the SIP PBX. I mean, the PMR obviously making live announcements, mobile devices potentially making or triggering pre-recorded announcements. The SIP server, which is going to bring us in any other communication from intercoms and also from other telephones throughout the building, paging stations and so on. So as you can see, it's quite a substantial variety of inputs that we're able to bring to bear all together. In summarizing this, really, you know, we kind of looked at this a little bit before. We're picking our systems according to the area that we're trying to cover. So smaller things for security fire brigade areas, technical offices, and then the bigger systems for the main areas. And again, looking again potentially at the input side of things. On the left-hand side, we have our gates, potentially flight information systems, control center, SIP, and so on. And then on the right-hand side, our PAVA and so on. So again, just showing how everything can integrate together to provide a complete, you know, a complete solution. It's important to discuss when we're talking about an airport that airports, although we've just dealt with quite a lot of upmarket technology, if we don't get the acoustic side of things right, you know, it's going to be a bit of a disaster. So we would like to think that where you've got airports with large volume spaces with extended reverb times, the design should probably include acoustic simulations to make sure you're going to achieve your intelligibility in the space. Very often when we walk around many airports, we'll see directional loudspeakers. So, you know, we would use a lot of our column speakers in those type of environments. So, you know, they're a fairly easy fix in a lot of airports where you can get them to the right level, and there are places to locate them that can be quite challenging, seeing them in totems and so on. So it is important to understand reverb time, but this isn't the time or place to go into this mathematics. I have to say that the sum total of this is that if you do the mathematics, the reverb time is adversely affected by having plenty of hard surfaces and by the growing size of the space, and the likelihood of success of a system is that the reverb time should really remain below 2 seconds to stand a good chance of getting an intelligibility of 0.5 or more. And again, what we're sort of saying here is, you know, if you've got a very high room and large spaces, you need to do these models. And there are different ways of achieving the requirement, and this is something that Ambient can help with. So we're quite used to the idea of doing modeling for projects. So this is sort of just a typical example airport terminal model, where the room is around about 10 meters high, 3,200 square meters of surface, and we've specified 36 line array speakers for that. and that gives us, you know, a good enough coverage. One of the things that we are also able to advise on is to look at the potential for what materials might be needed if there are material changes required. So although it's not our business to actually make these acoustic modifications, if we as a group are all involved with working with architects and so on, we can give them some help. So we're suggesting that once we do these models, we can suggest, for example, in this case, we've added some rock wall slabs positioned behind some baffles, and this is actually changing the RT time, and we can obviously help with those areas of design. And one of the things that's also very important when you look at these things is ambient noise, noise sensing. So again, just part of our acoustics acoustic input to this project, it's nice to manage the level of the announcements, because obviously a lot of airports change from being very quiet first thing in the morning, or you know, and very noisy during, say, school holidays time at a baggage belt, but then when there's no baggage there, it's very quiet. So using noise sensors to regulate the sound of the announcements to match the background noise level is really important. So we have these noise control features. So we have noise sensors going back to a controller, and then they input again via LAN to our PAVA systems. And so it's both important not to have the sound too low and not to have the sound too high. If you have it too low, obviously it's unintelligible, but if you have it too high, it's A, it's unpleasant, B, you know, you may be in an area where you're creating pollution which upsets your neighbors, and C, it actually decreases intelligibility. So the louder, if messages are unnecessarily loud, they create unnecessary reflections, and that's not beneficial to our intelligibility. Pretty much finally, and we're not going to talk about it today, but we do have our smartVES system, which enables us to more accurately maximize speech intelligibility by generating headroom in the bandwidths that we want that we want things in. So we're not pushing the whole level up and pulling the whole level down. We're able to consistently adapt our headroom octave by octave across the frequency spectrum. So it's essentially like having a live sound engineer working on the system all the time. So we're not going to talk about smartVES today. That's a subject for another day, but it's there all the same. And so when we come to our conclusions, because it's coming to that time, we believe that the public address and voice alarm systems are vital in the efficient running of an airport for both passenger comfort and life safety. But unusually, the public address system does not exist in isolation, as we've seen today. You know, actually linking around to a whole section of other systems around it means that we're maximizing its use. We're conveying that information across the management spectrum and helping out our travellers as best as possible. And then use SIP can be very handy in terms of your install times. Consider segmentation if you've got a larger airport rather than a smaller airport. And when you're making your planning, don't get too carried away with all the technology and then realize that you've put all the wrong speakers in at the end. So don't forget the acoustics. And with that, and given that our time is pretty much up, I'd like to thank everybody for coming and attending. It was lovely to speak to you all. If anyone has any questions, we could do a question or two before I have to go.